Okay, this is part 6 of the lecture on using GLHEPRO for ground heat exchanger design. I'd originally thought we'd come back and do a live demo, but I think I'd just like to talk about sensitivity to a few different things. I think it's probably easier if I don't try to do it live. So settled on this as a base case, the 92.5 degree Fahrenheit maximum heat pump entering fluid temperature, and which resulted in a design depth of 303.5 feet. And so this is the main screen, and then the borehole resistance parameters. So we had adjusted the grout to give us the value that matched our in situ test. Okay, so as a first sensitivity analysis, I just looked at something we'd looked at a little bit, which is the sensitivity to the maximum heat pump entering fluid temperature. So our design case was here at 92.5, but if you look, as you get further from the undisturbed ground temperature, you need less and less borehole depth, but of course you have lower and lower heat pump cooling capacity and lower and lower energy efficiency. If you go the other direction, right, which say down to, what do we go to, 85 right here, we get increased efficiency, but we also need a lot more borehole depth, so we need about 400 feet. So there's usually, well, there probably is an economic optimum for every case. But there are other things, like you're going to be limited by what your local drillers or your drilling contractor can do, or what what the drilling contractor finds feasible to do, and so on. So okay, then I looked at a few other things, like I switched from the corrected heat pump to the uncorrected heat pump. If you use the uncorrected heat pump, then, which I'm not suggesting you do, I think the corrected one would be more appropriate, but it would have been about a 2% error. Now it's predicting you need 2% less borehole depth. If you use spacers to get the C spacing, maybe we'll take a look at that. All right, so if we'd gone back to borehole thermal resistance here, and we changed the spacing to C, this spacing here, and we pushed the tubes against the outside wall, we could have saved 8%. But there's a really good chance, or I think it's very unlikely, that you could install the boreholes, that you would find you save 8% on the cost, because the extra labor and time associated with putting the spacers on and dropping them down hole and so on just means it's unlikely that you're going to get this economic savings, even if you get the drilling savings. Okay, we used a measured undisturbed ground temperature of 63.55, which I think is, as far as well, based on our many measurements that we've made out at the site, I'd say it's quite reasonable. The Shing and Spittler model predicts about 62.5 degrees, right? And the difference there is about 4%, right? And the Shing and Spittler model is not perfect either. It doesn't really know the history of where your ground, and by history I mean a long time, hundreds of years. So, okay, now this is rather interesting to me. I think we might have started with 20 and we went down to 25 foot. So this is a sensitivity to the spacing. Now, just for sake of completeness, I went all the way down to 10 feet, which I don't think you could find anybody to recommend 10 feet these days. There was a time when some people were saying, oh, 10-foot spacing is good. You can see that if you go down to 10 foot, you're going to need an incredible amount of, or a very high depth, 780 feet, right? And so we had sort of settled as 25 feet, and that gave us a borehole depth of 303.5. But if you have the room, if you went all the way to 50-foot spacing, you would save about a third on the required depth. Right, so it's in this case, where we have a high ratio of annual cooling to annual heating, right, then there's a very high sensitivity to the spacing. Right, and of course, if they're balanced, we won't see quite the same effect. But this one's rather out of balance. So this suggests a general strategy, and maybe we should say a general strategy for cases that are heavily imbalanced, of maximizing the spacing and assuming that you are constrained by a fixed land area at the surface. You know, there's a certain place on the property that you have to put the boreholes, or at least you have to put them on your property, not on someone else's. The strategy would be to decrease the number of boreholes while increasing the spacing. So I looked, you know, we have a 12 by 10 base case, right? That means there's 11 25-foot spaces in one direction and 9 in the other, so that's 275 feet by 225 feet. Right? And we had then 36,420 feet total drilling. It may not have been quite that. I just multiplied the 303.5 by 120 boreholes. But if we went, for example, to something that would fit in the same space, and I just tried one case, a 10 by 8 case, you could go to 30.6 spacing, and you're constrained in one direction or the other. Actually, you could, if with a 10 by 8, you could probably have 2 different spacings, although GLHEPRO at present doesn't handle having different spacings in the X and Y directions. So that would give us 32,500 feet of drilling, or an 11% reduction. So that's not bad if you can go to 400 feet. But it's, you know, you'd have to get your drilling contractor to give you an actual estimate of the difference in cost for the two solutions. Other strategies, as we already looked briefly in the live demo, we could use a hybrid ground source heat pump system. That's likely to be, well, it's likely to be the case that if you can use a hybrid ground source heat pump system, it'd probably be hard to beat on first cost. You could make use of excess heating. It's an office building, so I'm not sure that, you know, there's necessarily a lot of opportunities come to mind, but if there is a restaurant, cafeteria, right, if you make the hot water with heat pumps, that would be one way to use the excess heat. If you have a parking lot that needs de-icing, that would be another possibility. This is Oklahoma, so maybe that might be hard to justify. Another intriguing possibility, in a paper published by one of my colleagues at Lund University in Sweden, he and his team were designing a school in Oslo, Norway, and he basically showed that by adjusting the building envelope design, you could do that at the same time you adjusted the ground heat exchanger size to get an overall optimum solution. Now there he had the opportunity to change the windows, right? And so what that did is, if you put windows with a lower solar heat gain coefficient, you would get lower cooling loads but higher heating loads, if I remember right. Yeah, I mean that should be correct, assuming the U factor of the window is the same. Right, you decrease the solar gains and you'll get lower cooling loads and higher heating loads. So it could be that in that location there's more flexibility to do that, and I have not gone into the Energy Plus file to see what solar heat gain coefficients are used, but that could be an interesting thing to check. Right, if you use a low, again, if you can decrease the amount of solar gains here, you may also save energy and reduce the size of the ground heat exchanger required. Okay, so that's it for this example.